Quantum mechanics has its own fascinating logic, its own internal coherence, and is experimentally verified, so it would be a shame to think of it as a series of random rules. What is L, and why can't it equal M? Why can M be negative if L can't be? Who are these guys? And then we get 4 more of them. So what deep insight does quantum mechanics give us? Well, it tells us that L might be D unless n equals 2, because then L can't equal 2, it can only equal S or P. Yet somehow these rules, along with Hund's rule and the Pauli exclusion principle, give us the periodic table of the elements and all the chemical properties of all the atoms in the universe. So maybe these rules aren't as arbitrary as they seem. This video is for students who have seen these electron configurations in a chemistry class and want some kind of conceptual backup for them. Of course, you could just dive into a quantum mechanics textbook, or maybe not. We'll start with a brief review to make sure everybody's on the same page, so if you are bored already, skip ahead to the 7-minute, 10-second mark. There it is, the final electron in lithium, 1s2, 2s1. Wait, I've seen this before. N equals 2, L equals 0, S orbital, M equals 0, spin up. And then there's iron, argon's filled shell with a 4s2, 3d6 added on. This is electron number 26. N equals 3, L equals 2, p orbital, M equals -2, spin down. We could also find other electron addresses. This is for number 9, fluorine's outer electron, but I already knew that. Just tell me what those numbers are and where their weird rules came from. Oh no, now he's going into the history of the atom. This video is useless. Wait, don't turn it off. I told you if you want you can skip ahead to the 7-minute, 10-second mark. But I'm trying to answer your question. Where did the quantum numbers come from? Well, where did Dalton's billiard balls come from? Did he just hang around in a pool hall? No, he noticed that the ratios of masses in different compounds reduced to simple whole number fractions. That's right, a ratio of ratios, right? I flunked chemistry. Thomson did not love raisin bread or plum pudding or whatever. He just needed a way to explain that beam of electrons and where it came from, the one he could control with electric and magnetic fields, you know, the first TV set. And they say that Rutherford discovered the nucleus, but he never saw it. He just needed a way to explain why alpha particles kept bouncing back at him. Do quantum orbitals sound weird to you? Well, Rutherford said that the atom is mostly empty space. Now that's weird. And no one ever took Bohr's model seriously. First of all, is this thing even three-dimensional? But it did explain where the emission lines of hydrogen came from. It even predicted new ones. So each model has experiments and weirdness associated with it, and new physics too. Thomson used laws for electromagnetism. Bohr used Planck's quantization and his equation for the energy of a photon. See that H? It's Planck's constant. You'll see it a lot. Most times, though, we'll talk about H bar, which is H divided by 2 pi. Speaking of new physics, the quantum mechanical model satisfies the Schrödinger equation. Psi is the wave function, or probability function. Also in this theory, we can't simply measure values. Instead, we'll have to have an operator act on a wave function. Think of it as multiplying a matrix by another matrix. More on that later. So what experiments go along with this new model? Well, we'll get to a couple in a bit, but the quantum mechanical model does what the Bohr model can't. Besides predicting and explaining even more spectral lines, the quantum mechanical atom can predict the shape of molecules and the strength of their bonds. So, our task will be to get here from the simpler Bohr atom, with its stable orbits and its electron transitions. To do this, we will use the analogy of planetary orbits. You could say that what happened in the 20th century with electrons mirrored what happened in the 17th century with planets. They went from the circular orbits of Copernicus and Galileo to the ellipses of Kepler and Newton. It's a terrible analogy, but it's the best one we've got, and it's bad for 4 main reasons. First, the electrons do not orbit the nucleus. That sounds odd, but they can't. What's the alternative? You can think of them as a swarm of fireflies on a dark night. You see the lights blinking on and off, now here, now there, but you can't follow the path from point A to point B. The difference is that there really is a path for the firefly. There really is no orbit for the electron. Because of the Heisenberg uncertainty principle, it says that you cannot have simultaneous values for the exact position and momentum of an electron. Remember how we said that measurement is a bit different here in quantum mechanics? Well, measurement is not passive anymore. It's an operation on the wave function that affects the wave function. Think about it this way. If you measure the momentum of the particle and then its position, you'll get a different value than if you measure the position and then the momentum. This uncertainty is small, but for us, it's a big deal. Second, A planet's distance from the sun, its velocity, and its orbital energy can all vary continuously. For electrons, these values are quantized. Certain values are possible, in-between values are not. Think of the possible standing waves on a string. Only certain frequencies and wavelengths are possible. Or think of the volume controls on a TV remote. Up 1, up 2, up 3. Compare that to a knob. Number 3 is the angular momentum of the system. This is the biggest shortcoming of our analogy, and I'll tell you why in a second. But first, hey, angular momentum, neat. L, the angular momentum quantum number. It gives you the angular momentum of the system, right? Well, not really. Also, the quantization of angular momentum of the atom. That's something that we inherited from Bohr. Remember those quantized orbits? Where did they come from? Well, they came from insisting on integer numbers of de Broglie wavelengths in each orbit. A little mathematical rearranging will turn that into the quantization of angular momentum. Hopefully you've checked out the mathematical guts of the Bohr model on your own. They're really not that bad. Hey, look, on the right. It's h divided by 2 pi. That's h bar. Anyway, quantized angular momentum, which is, in a way, also true for planets. What I mean is that an individual planet's angular momentum never changes. The gravitational force exerts no torque on the planet, even as it speeds up or slows down. So, why is that a problem for our analogy? Because a planet's constant angular momentum is directly linked with its total orbital energy. That's not true for electrons. An electron's angular momentum and its total energy are still friends. They're just not joined totally at the hip. Fourth, the reason our analogy is bad is that electrons repel each other. When multiple planets are in a solar system, it does not matter. 99+% of the mass of the system is still in the sun. The nucleus also has 99+% of the mass of the atom, but we're interested in charge now, and those electrons are repelled by each other just as much as they are attracted by the protons. That's why the Bohr model only worked for one electron atoms. Okay, with all that as background, let's try to answer the question, what are these numbers, and how come these rules? N, the principal quantum number. It tells us how much energy the electron has. These energies are quantized, just like in the Bohr atom or in the solar system. But there is no reason to draw these orbits like this. These orbits are just as good. Like the circular orbits, they have different energies, but they also have internal complexity. The planet speeds up and slows down, but the total energy, potential plus kinetic, remains constant, just like in a spring mass system. 3 things about this. 1, values should be quantized. Number 2, we no longer separate potential and kinetic energy. One is based on position, the other on velocity. Heisenberg says not at the same time, no way. Number 3, the total energy of this system can never fall all the way to 0. More than that, neither the potential energy nor the kinetic energy can ever be exactly 0. Again, thank you, Heisenberg. 0 kinetic energy or 0 angular momentum, that would mean a perfectly stationary electron can't happen. 0 potential energy can't happen either. Oh, wait a minute. Oh, can it? A pendulum moves through its lowest point. A spring moves past equilibrium. A planet could swing, quote, right past the star. Potential energy goes to 0, right? Sure, but electrons don't orbit. Get that through your head. A pendulum or a satellite could have gauges showing its position, its velocity, its kinetic energy, all these different values steadily changing. Electrons can't do that. Or think of it this way. If you knew that the electron was, quote, right at the nucleus with all of its energy, kinetic energy, then you know its location and its momentum simultaneously. And that would make Heisenberg very angry. So much for the spring. 1 quantum number down. Oh, look! And we said that energy can't be 0 and n can't equal 0. Neat. The second one is more difficult, though. The angular momentum quantum number, or orbital number. Think of it as telling you how much of your energy is kinetic, which is exactly what I told you we couldn't do. Well, we're going to do the next best thing. For the electron, we'll talk about its angular momentum instead, and we'll talk about it using this operator. To be specific, the operator shown here gives the square of the angular momentum. More on that later again, but you're on warning, second quantum number. Prepare to be squared. In the meantime, let's just let this operator go to town on that eigenfunction. You know, the one representing our probability function. It will kick out an eigenvalue and we'll be good, but things just got weird. We'll return to classical physics in just a second, but first let me tell you that the L quantum number is related to the total angular momentum in a complex way, which we already got that. No, look at the equation. Notice that the angular momentum, big L, is not zero, even if the angular momentum number, little l, is zero. So from now on, if I say big L, I'm talking about angular momentum. If I say L or little l, I'm talking about the second quantum number. So let's get back to planets. You're saying that finding the electron's L is like finding the planet's kinetic energy, right? Sorta. Again, this is where the analogy is the weakest. A planet's angular momentum does not change, but its kinetic energy does. Well, question, if the planet's angular momentum is conserved, why isn't the electrons? Because electrons don't orbit. Anyway, we can all agree that kinetic energy and angular momentum squared have something to do with each other. But now the question is, why must L be less than N? Answer, because we can't have more kinetic energy than our total energy. That's one way to think of it. There must be some limit to total angular momentum, and that limit is based on total energy, and we are half done, so let's summarize. N, the principal quantum number. How much energy do you have? Are you a small orbit or a big orbit? L, the angular momentum quantum number. How much of that energy is kinetic? That's what we'd be asking if you were a planet. Are you close to the sun with more Ke or further out with more Pe? For the electron, we talk about angular momentum squared, which doesn't change for a planet. Sorry. But again, we're letting Ke move around for the planet and L squared move around for the electron. So that sounds fair. Next, on to the third quantum number. Azimuthal angular momentum. It tells us how much of the total angular momentum is in any particular direction. We'll pick Z for planets. This is not much of an issue because all the planets not named Pluto orbit in the same plane, but swarming electrons orbit in all three dimensions, which we can show with the right-hand rule, X, Y, and Z. Notice the counterclockwise convention. An electron with a clockwise orbit... I almost said orbit! Shame on me, a clockwise-ish momentary velocity. That would give us a negative value for big LZ. And this is why m is greater than or equal to negative L and less than or equal to L. It also shows why we're interested in angular momentum squared. For example, let's say you are in the p orbital. Small l equals 2. Then big L is root 6 bar. Quick! Square it. Total angular momentum squared, big L squared, 6 bar squared. M has limits. The leg of a right triangle cannot be greater than the hypotenuse. Oh, wait a minute. I got an idea here. Let's say that m equals 2. That would mean big LZ equals 2 bar. Now let's look at our equation for big L squared. And one way that would work is if big LX and big LY both have m values of plus or minus 1 bar, right? Wrong! Totally wrong. You can't say that. Heisenberg won't let you. Just like you aren't allowed to know the position and the momentum simultaneously, same thing goes for LX and LZ. If you throw that LX operator on your wave function, it's going to change the wave function, and then you'll get a different LZ value when you do the LZ operator. You can't do it. Taking, however, the L squared operator and the LZ operator, those commute, so those can be done simultaneously. Heisenberg gave you the thumbs up on that one, and I knew you were worried about that. But can any of this really be seen experimentally? Yes, it's called the Zeeman effect. Take one of those electron transitions that Bohr was famous for, then do it inside a magnetic field. The one emission line splits into 3. The p orbital is L equals 1, so we have 3 possible values for m, -1, 0, 1, and these 3 different orientations interact with the magnetic field in different ways. In order to discuss exactly how these energy levels will increase or decrease, we'd have to go back to our model for the quantum oscillator interacting with photons, and I don't want to do that, but we essentially have loops of current around the atom. I did not say orbits, I said loops of current around the atom, and that means the atom itself is like a magnet, like a little compass needle. And what is true of the atom with its electrons is also true of an individual electron. This is called the dipole moment of the atom and the intrinsic dipole moment of the electron. Turns out the electron still acts like a little magnet even if it's not, quote, moving in an orbit, unquote, which isn't really an orbit. The electron itself is a point particle and can't really spin, but it acts like it does, either spinning up or spinning down, either adding to or subtracting from the total magnetic moment of the rest of the atom. It's our 4th quantum number. And yeah, it's weird, but it's our explanation for an experiment. Electrons were shot through a magnetic field. Some were deflected up, some were deflected down, like they were a bunch of tiny little magnets pointing in one direction or another. And we're done. So let's take this analogy back to our two old friends, lithium and iron, and see what happens to them. Lithium, you are in the second energy level planetary orbit. You don't have an angular momentum though, which means you can't obviously have any angular momentum in the z direction, and you are spin up. And there you are, medium-sized orbit, that's your n value, no angular momentum, and we celebrate that by placing your planetary orbit where the kinetic energy is least. And next is iron. Wow, n equals 3, that's a huge orbit. And this guy has lots of angular momentum, L equals 2 and M equals negative 2, so all that angular momentum is in the negative z direction, and you are spin down this time. Notice that we jump to the next planetary orbit, and we are celebrating this electron's angular momentum by putting it where the planet would have max kinetic energy, but poor planet, it has turned its orbit around. Yes, planets do have orbits. This planet's orbit has been turned around, is going clockwise, not counterclockwise, and the seasons are going backwards, which is sad. And we're done. We have a periodic table and electron configurations based on those four quantum numbers, and they're extremely logical, completely non-arbitrary rules. To review, N is the total energy. It's a positive integer because energy is quantized and cannot be zero. L is the angular momentum or orbital quantum number. You can think of it as telling you how much of the electron's energy is kinetic, or what the angular momentum squared would be, and don't forget that even if little l is 0, big L, the angular momentum of the system, is not 0. M tells you what percentage of your total angular momentum is in the z direction, so the magnitude of LZ is limited by the total amount of angular momentum, and electrons have been caught red-handed acting like tiny magnets. Great. So what about those shapes? Well, that's another kettle of fish altogether. We'd need to explore those wave functions in detail and in spherical coordinates, which is not something that we can model with our planets, but something that is, in principle, solvable.